In this illustration, we intend to simulate the one-dimensional consolidation of a fully saturated soil layer in the Abaqus software. The simulation is aimed at drawing a diagram of soil consolidation settlement. Actually, we intend to simulate the example 4.2 from some Helvani book in the Abaqus software. The behavior of soil is in elastoplastic mode, and here the model of camp clay has been utilized for defining the plastic properties. I will enter the Abaqus software for simulation. I will click on Create Part. I intend to create geometric shape of soil. I will select the modeling space as axis symmetric. Here I'll select deformable and shell. Enter the rough size of the tracing page as 0.5 meters and continue. Here I will draw square. The soil is in form of a cylinder with a diameter of 20 centimeters and height of 10 centimeters. I will enter the height as 0.1 meter and the radius as 0.1 meter too, and click on Done. In the next step, I will enter the property module. Click on Create Material. Here I intend to define the properties of clay. I'll select Density from General menu. The density of soil is 1923 kg per cubic meter. In the next step, I'll select Elasticity and Porous Elastic from Mechanical menu. Load bulk modulus that is displayed by kappa is equal to 0.01957. The Poisson ratio is equal to 0.28 and tensile limit is equal to 0. In the next step, I'll select Plasticity and Clay Plastic from Mechanical menu. Here, lambda is equal to 0.1174. Stress ratio is equal to 1. Initial yield surface size is equal to 4.595 kilopascal. Wet yield surface size is equal to 1 and flow stress ratio is equal to 1. In the next step, I'll select Pore Fluid and Permeability from Other menu. Here the coefficient of permeability is equal to 6 multiplied by 10 to the power of negative 9 meters per second. And void ratio is equal to 1.5. The specific weight of water is equal to 9,810. And finally, I'll click on OK. Then I will click on Create Section. From here, I'll select Solid Homogeneous and then Continue. Here, I will click on OK. Then on Assign Section, select the soil, Done, and OK. In the next step, I will enter assembly module, click on create instance, and then on OK. Then I will click on translate instance, select the soil. First I'll select this point and then the origin of coordinates and done. In the next step I will enter step module. This question will be done in 3 steps. I'll click on create step. The step 1 is for applying the seating pressure. I will select geostatic from here, continue. The analysis would be in non-linear form. From here I will select automatic and click on OK. Step 1 is used to create equilibrium in the clay layer. I will click on create a step. In the step 2, a sudden pressure is applied to the top surface of the soil. Here I'll select the soils, continue. Here the time period is equal to 10 seconds. Here I'll enter max pore pressure change per increment equal to 21,000 Pascal. Here I will select unsymmetric, enter initial increment size equal to 1 and OK. In the next step I'll click on create. The step 3 is a consolidation step. From here I'll select soils and continue. Here the time period is equal to 100,000 seconds. Here I will enter maximum number of increments equal to 1000 and initial increment size equal to 100. Maximum pore pressure change per increment as 17,000 Pascal. Select unsymmetric here and OK. Here I will save the model. Enter load module, click on create load, select geostatic seating pressure step, and then select pressure here and continue. Then I will select the top surface of the soil and done. As explained in the book, in the step 1, the seating pressure as much as 9.19 kilopascal will be applied to the top surface of the soil. 9.19 multiplied by 10 to the power of 3 Pascal. I'll click on OK. I'll click on create load again. Here I will select pressure loading step. Here pressure and continue. Then I will select the top surface of the soil and done. In the step 2, a sudden pressure as much as 20 kilopascal will be applied to the top surface of the soil. Here I will enter 20,000 Pascal and put amplitude on instantaneous and OK. In the next step, I'll click on Create Boundary Condition, select Initial Step from here, then Displacement Rotation and continue. I will select this line and Done and close the boundary condition of U1 for it. I will click on Create Boundary Condition again, select Displacement Rotation from here and continue. Then I will select the bottom of the soil, Done, close the boundary condition of U1 and U2 for it and OK. I will click on Create Boundary Condition again, select Symmetry, Anti-Symmetry from here and continue. Then I'll select this line and Done. Actually, this line is the axis of symmetry of the model. I'll select X symmetric from here and OK. I will click on Create Boundary Condition, select Consolidation step from here, then select Pore Pressure and continue. I'll select the top and bottom surfaces of the soil and Done. As explained in the book, the top and bottom surfaces of the soil are permeable and there would be the possibility of drainage from these surfaces. So I'll put the pore water pressure on 0 and OK. In the next step, I'll click on Create Predefined Field. From here, Initial Step, select Void Ratio here and continue. Then I will select the soil, enter Initial Void Ratio equal to 1.5 and OK. In the next step, I will click on Create Predefined Field, select Geostatic Stress from here, continue, select the soil, and Done. Here, the stress on the top surface of the soil is equal to negative 9.19 multiplied by 10 to the power of 3 Pascal, and the height of soil is equal to 0.1 meter. The stress on the bottom of the soil is equal to negative 9.19 multiplied by 10 to the power of 3 Pascal, and the height on this part is equal to 0. I will also enter the lateral coefficient equal to 1. The quantity of 9.19 multiplied by 10 to the power of 3 Pascal is the same seating pressure that is applied to the whole of the soil. I'll click on OK, enter Mesh Module. Here I will select Seed Edge, select these two lines, Done. And consider 12 elements for it. Then I will select these two lines, Done, and consider one element for it and OK. Then I will click on Assign Mesh Control. From here, select Structured and Code and OK. I'll then click on Mesh Part and then on Yes. I will click on Assign Element Type, select the soil and Done. I will put the element family on Pore Fluid Stress. Here select Quadratic and OK. Here I will save the model, then enter the job module, click on Create Job. Continue, OK, and click on Submit. The analysis was done successfully, so I will click on Result. Here we intend to draw this diagram. Actually, we intend to draw the diagram of the consolidation settlement of soil. To do so, I will click on Create XY Data, ODB Field Output and Continue. From here, I will select Unique Nodal, then select U2, select this node, and click on Save As in this manner. In the next step, I will click on Create XY Data. From here on Operate on XY Data and Continue. I will then select this diagram and multiply that by 1000. In this manner, the unit of displacement will be turned to millimeter. In the next step, I'll right-click on the diagram, edit, select these two columns, copy, and paste them in the Excel software. The first column is time period, the unit of which is second. The second column is settlement, the unit of which is millimeter. In the diagram having been drawn in Sam Helvani book, the unit of time period is hour. Actually, 1 hour is equal to 3600 seconds. So I will divide the quantities in this column by 3600 in this manner. The first column is time period, the unit of which is hour, and the second column is settlement, based on millimeter. The diagram having been drawn in blue is the one obtained from the Abaqus software. As you observe, the results gained from the Abaqus software are quite the same as those in Sam Helwani book. Here, the final consolidation settlement of soil is 4.9 mm.